Okay, welcome to the second day of the math camp. We'll just pick up where we left last time, which was we were about to talk about series very briefly. The reason I'm talking very briefly about series is not because series is not important. It's also a very important concept. But the reason I'm very brief about it is because firstly, we don't have much time. And the second reason is because series, in a way, is like just like a special case of sequences. So basically, I'll talk about why that is so. But since it's also important, if you want to know about more about series, I recommend you to check the textbooks about it. Although probably you should be already familiar with it because you already took like calculus classes. Usually, the second semester of calculus, you usually learn about the sequences and series and convergences. So I'm just going to be very brief about this part. So, although we have a different name for this sequence called series, it's not really different because it's just basically like a new type of sequence. But the thing is just we just sum all the sequences. So what does it mean is that I have a definition right here. So you can see the definition of a series, which says that, so if we are given some sequences, so it's like an AN sequences, we kind of write it as like that. Can you see it? Like the summation notations? I'm pretty sure you're already familiar with it, right? Anyone who doesn't know the summation notation, right? Everyone knows it, right? So it basically means like you're summing up all the elements from P to Q, where Q is, of course, it has to be bigger or smaller. I mean, it has to be bigger or equal to the P. So it's like basically we're like summing up all these sequences from some part to one part. So for example, like, so let's say like P is like 5 and Q is 9. So it's like, this. And basically what this is saying is simple. It's just going like, you're just like adding up the sequences from A5 to A9. So that's the notation there. It's a summation notation. Although we don't usually call this notation series, but this is like very nice reminder to know about the overall process of series. So it's there. And we usually denote this as either right below, like AP plus 1, and on until we add up AQ. So with the sequences, so we're making like a new sequence. So for every sequence AN, we are associating a new sequence called SN, where the SN becomes like we add up all the sequences AN sequences from 1 to N. So you can see the notation here. So basically, the reason I say the series is like just a new special case of sequence is because you can just denote it like this. So as I said, you just change it from 5 to 1, what you get is, so when you say you're adding up the sequence AN from 1 to Q, you're basically getting this sequence, this summation where you're just summing the A1 sequences from A1 to AQ, and you can just denote this as SQ, right? So for every Q, you're just adding up until the number Q. So this is just like making a new sequences out of what already was a sequence. So just like basically just like a special case of a series you can make if you have a sequence already. So it's nothing that's very different. So it kind of works similar to the case of the sequence, except it's just you're just summing up every time for every indexes. So just remember that. And when, of course, because it also talks about like, because n can go to infinity, you can also make some sort of limit connotation into it. So when n goes to infinity, we use the notation here, which says like the summation from 1 to infinity, right? So AN, you're adding it until the end. And this last notation is called the series. So when you say series, you usually refer to the part in the last part where you're just having a sequence and you're just adding it all up from 1 to infinity. So you should remember this. So usually when you have the sort of summation part of a sequence, you call this like a series. And there's also a lot of part about how whether some series converges or not. But in a way, it's very similar to the concept of how you used to define the limits of the sequences, except it's just in a series notation. So just keep in mind. That's why I'm being brief about it. And this is basically what I just said. So as you can see, the series is like same as sequences. So it's just like a sequences where each term is added up. So limit also holds similarly. So to further know about how like limit works in series, I wrote in the slide. You can check Rudin's PMA or any other calculus books you can find. They'll have all parts and sections about series and how it converges. So you can also check about it. Like, you probably should be already familiar with like concepts you might remember from calculus, like root tests or ratio test stuff. It's kind of related to how series converges. Kind of you can show how it converges, but I don't think it's like that important, at least in a economic course in math camp. So I didn't put it in. But if you want to know more about it, you can just check the textbook. This is just like a very brief exercise I put. So basically, this is one of the questions you can solve. It's an exercise I wrote. It's not mine. It's from a textbook. If you solve Rudin's book, you might remember this. This is like 1 or 2 second question there. So I'll give you some time. So try to solve this. I'll give you the maybe like the sketch of the proof after the next session. And so after that, I'll talk about it. So I'll give you some few minutes so you can try this. To give you some like tip, try to use remember the monotone convergence theorem? Like this one. So basically, remember like what we said was that if the sequence is, because like sometimes it's very hard to define whether sequences converges like using the direct definition. So what we try to do is like we have this nice theorem that we can use to kind of shows like it's equivalent to saying that it has a limit, right? And MCT is like one of the very useful theorem where you just need to find that as long as the sequence is monotonic and the sequence is bounded, if you show it's monotonic and bounded, you can show immediately that it converges. So you kind of note that, I don't know, I mean, it's not that intuitive, but you might think it might be easier to think about the monotonic convergence theorem because you can kind of see that this sequence seems to monotonically increase. And plus, the sequence seems to be bounded. So what I would suggest is that the easiest ways to do it is try to use the monotonic convergence theorem to kind of show that it holds. Then if it holds, then we can automatically show it converges. So very interesting about proof-based mathematics and analysis is that in a lot of the calculus courses, we're really thinking about mostly about where it converges. So like we just kind of calculate stuff. Like we calculate like if we kind of already assume it converges, and we just like write it down the answers and just multiply and get the like answers. Like if I remember right, like in very basic calculus courses, what you would do is that instead of finding whether it converges or not, we'll kind of already assume it converges, and you just find like what sort of limit it has. So like you should go like, you know, it might be more familiar. You would do something like this. But when you solve it where this converges in basic calculus course, where you say like this goes to S and this goes to S, so you just go like this, and then you do like a square notation, something like this, and you just make some equations solve where what S is. That's like the most basic calculus courses. But if you want to solve this in like more rigorously, this is problematic because when you do this, you're already assuming that the SN converges. But we didn't say anything about SN really converging. So if you want to do this sort of procedure, you must first show that SN really do converge. Then you can do this sort of techniques. So that's why we're doing this. So I'll give you some 5 minutes to try to solve it, and we'll have some quick break for 5 minutes, and then after we'll come back and I'll talk about this exercise.